Alright, well, so it's time for a nap after that great lunch, but let's talk about some physics. So actually, I realized after listening to Andy that the topics he's covering will be covered tomorrow are very closely related to what I'll be talking about today. As he mentioned, he's going to talk about appearance of superconductivity, D-wave superconductivity is similar due to antiferromagnetic exchange interactions. And that is basically what I talked about today. But it'll be a very different language, and so perhaps you can put the two together and get deeper insight. So as I said in my first lecture, the overall theme is to talk about the onset of antiferromagnets, antiferromagnetism in different materials, and I gave the very simplest example of the onset of antiferromagnetism in this model of coupled dimers, which is an insulator, for which we have a fairly complete theory. And I also mentioned briefly that if you take a frustrated square lattice antiferromagnet, not just the dimerized one, then the issue of what happens at the antiferromagnetic critical point is a lot more complicated, and you have to worry about other types of broken symmetries and topological orders in non-magnetic phase. So that's something I will not touch at all. But now I want to turn to the question of what happens when you have the onset of antiferromagnetism in a metal. And we have now many beautiful examples of systems that do precisely this, especially two-dimensional systems, the iron-based superconductors and also the electron-doped superconductors. So for the most part, you can keep those in mind, and tomorrow I'll talk about extending these ideas to the whole doped cuprates. Okay. All right, so I'll have actually quite a few calculations that are on the slides. All the factors of I and everything will be correct, and you would probably get a printout of those, I presume. So just to be definite, let's just talk about the Hubbard model. We have electrons hopping on, let's say, the square lattice with just on-site repulsion and some chemical potential. And then, to mathematician, then this is the complete definition of the model. These are just operators which obey these relations. But there's just enormous richness on what even this very simple model can do as part of it. So I'm not going to solve this, but I'm just going to make a guess that this, from this starting model, under certain regimes that you get different types of phases and then try to make general statements in the structure of those phases. Whether those phases actually occur for the Hubbard model is a separate question, which obviously the approximate methods I use will not be able to answer. So let's start with u equals 0, where I have some just free electrons hopping on the square lattice. And for the electron and hole doped cuprates, they'll lead to these two views of the same Fermi surface. It's exactly the same view. The gamma point here in the center, here the gamma point is at the corner. Gamma refers to k equals 0. And then you have a Fermi surface separating the occupied states. In this case, the occupied states are outside and the empty states are inside. So when you just take free electrons, you have something called Luttiger's theorem, which, well, if a free electron is not really, doesn't even deserve the word theorem because it's kind of obvious. The total number of electrons is equal to the total number of occupied states. And the number of occupied states is just proportional to the area in momentum space. So you look at the area in momentum space, and that gives you this value. And so that area enclosed by, I guess, A, so what is the area of the occupied electron states? That's the area of these states here, that's A sub E, is equal to 1 plus P, where P is the electron doping, or 1 minus X, where X is the hole doping. So it's just the counting of electrons and holes. So when this becomes a theorem, was Luttinger showed that, and others, that to all orders in perturbation theory, in something like the coupling U, this still holds. This is exactly true. There's still a Fermi surface, which is the boundary in the region of momentum space where you go from quasi-hole to quasi-particle excitations, and that boundary encloses an area given by the density of particles.
When you say area, you mean so 2 dimensions area, volume, and 3 dimensions.
Yes, exactly.
Right.
Yeah,
As
so
opposed to area. It's not surface area. It's the
yeah. So basically the number of occupied states in d dimensions, ddk over 2 pi to the d. That's the total number of states that you're occupying per unit volume. Then you put in a factor of degeneracy of 2 for spin, and then you say this is k is less than kf if it's a spherical Fermi surface, and this should be equal to density of electrons. So that's a simple relation that appears for free electrons, and this relation is also true for interacting electron system exactly. There's a little bit of subtlety in how you define kf. As I said very quickly, it's defined by where the excitation spectrum changes from quasi-whole to quasi-quark, as in the free electron case. Okay, so now what we want to do, we want to take such a metal with such a big Fermi surface. So this is now a non-magnetic state. So this is, for the insulator, we have to work a little hard to get a non-magnetic state. We have to take this dimerized system, have the spins form a singlet, and you got non-magnetic state. Here, the thing is, this free electrons are non-magnetic on their own because each state here has both up and down spins. Each electron here has both up and down, so the net spin is 0. So this is a paramagnet, it's a Pauli paramagnet, it has some susceptibility associated with it. Okay, so now what we want to do is we want to add some interactions, for example the Hubbard interaction, and be in a regime where you get antiferromagnetism. So I imagine that somehow due to some collective effect, the antiferromagnetism is going to develop. So if I look at the average value of the spin operator, here S is just the electron spin operator. So S is just C dagger, C on each side, say. And if you look at its average value in an antiferromagnetic metal, then it will have a modulation e to the I k dot r. And the coefficient we're going to be phi, and it's a vector phi, and this is our antiferromagnetic autoparameter. So this phi is in fact exactly the same as the phi I introduced this morning as the coordinate of the rotor. Here, as you'll see, I'm going to introduce it in a very different way, but have the same physical interpretation. So so we want to understand what is the interaction between this antiferromagnetism and this metallic Fermi surface. So we add in the U, so this is how formally you get this phi field. You take your Hubbard interaction on each side, and just by some operator identities, you can show that this is equal to this, where S squared is just that operator S squared. So this is true for independent of the electron state on that side. So it's an exact operator identity. And then you take this this identity and you insert it in the path interval for the electron. So the final path interval for the electron has this Hubbard interaction. You use this identity, and what you get is get this S squared on each side. Then you do this famous Hubbard-Stratanovich transformation. You introduce on each side and at all times tau another vector field I call J, which is written with just an auxiliary variable, because if you look at this integral here, it's just a Gaussian integral over J. So if you do this integral by completing the square, you'll get back this up to an overall constant, which I absorb in the definition of this path integral. Okay, so you just complete the square, you get J minus S something squared plus an S squared term, and that's all chosen cleverly. So you get this exactly 2u over 3 factor over there. So no approximation so far. Okay. So now we have to do our model involves the electrons. So in terms of a path integral, I have an integral over the electrons over J of some Lagrangian. And the Lagrangian has some Lagrangian for the electrons, which I'll specify in a bit. And it has this 3j squared over 8u. And then I have minus j times c diagonal sigma c. This is just a Hubbard model rewritten in a funny way. No change so far. Okay, now obviously I can't do this in a row. It's too hard in general. Yes?
Isn't there some sort of constraint on the spin there? So should be 0 or 1? Or?
Yeah, because that constraint comes automatically from this.
Okay.
So you have one electron. You have only a single. On each side, you either can have 0, 1, or 2 electrons, and so the spin has to be either 0 or 1/2. When that's another quick way to derive it. So this term I've written, if there's 0 electron, this is u over 4, because this is 0, this is 0. If there's 1 electron, this is 1/2, 1/2. It's also, if there's 2 electrons, and up is 1, and down is 1, so this is u over 4. So whether there's 0 electrons or 2 electrons, it's u over 4. Now for 0 electrons or 2 electrons on the same side, the spin has to be 0. So this term is 0, so that's correct. Now if there's only 1 electron, this term is 0. Oh no, what is that? Sorry. 1 it's minus u. There's only 1 electron here, this is minus u over 4, because one of these is plus 1/2, the other is minus 1/2. But if there's 1 electron, s squared is 1/2, so s squared is 3/4, and okay, you work it out, right? So that's how you can derive that. Or if you don't like that, you can actually do lots of anti-commutation relations and see it works. Okay, so now here I'm going to make a physical assumption. This is where I stop solving anything. I'm just going to assume that I'm in a regime of parameters where I want to become antiferromagnetic. And so I'm going to assume that the path integral is dominated by configurations of J. J can have an arbitrary dependence on space. But I'm going to assume the important configurations of J are where phi, but J is oscillating with this e to the I k dot r factor, where k is this wave vector k, which is pi pi. So I should have written that somewhere. This kind of antiferromagnetic structure has wave vector pi pi, so it oscillates very rapidly from side to side. So that's why I put in this factor. And then after that, I'm going to assume that phi varies slowly with space. That's almost exactly what I did for the rotor model. I introduced a phi on each dimer, and then I just assumed phi was uniform between the dimers to give me the antiferromagnetic state. And that's effectively what I'm doing here. So I plug this in here, and then finally, this is the kind of sometimes called the spin fermion model that I want to study a bit more. Now I realize some of you may not be familiar with path integrals for fermions, but I won't really use much of it, I suppose. I don't think I'm going to really use it. So this is, when you see this term, just think of that as the Hamiltonian for free electrons. This is just something that describes free electrons, dispersion Ek. So this term here is this coupling here. The phi is slowly varying. C is not necessarily slowly varying. C are the electrons with any momentum you want. And then there's an e to the I k dot r factor associated with every factor of phi. Now, for phi itself, I had the j squared term here. So I do have a phi squared term here. But now, just as I did for the rotor model this morning, I imagine that if I do a little bit of renormalization, or if I do some coarse graining, I will generate all kinds of terms in phi, including time derivatives and spatial derivatives and phi to the fourth terms. So that's exactly the kind of thing I did when I went from the rigid rotor model to the phi-4 field theory. Here also I have the same. So you see then, almost just by waving my hands a lot, I get the same theory that I studied this morning, theory for the rotors, for the onset of antiferromagnetism. But one very important difference is now this rotor is coupled to the electrons, and the electrons themselves have a Fermi surface. So what makes this much more complicated than this morning's story is that here in the morning, the only low energy excitations were the excitations of phi at long wavelengths. But now there's another set of low energy excitations. Those are the excitations of the electrons near the Fermi surface. And they're coupled to each other. And that's so the whole purpose of this lecture is to begin to try to understand what the effect of that coupling is.
Excuse me.
Yeah.
Hubble's current transformation is mathematical identity, and you're putting some physics
Yeah.
inside of your like mathematical identity. So what's the motivation you can do that, or because you have some assumption in this field already? Yeah.
Well, I mean, so as I said, my purpose here is to understand the theory of the onset of antiferromagnetism in a metal. My purpose here is not to solve the Hubbard model. I'm just using the Hubbard model as a guide, as a convenient tool to guess the kind of terms I should worry about. Okay? If I want to solve the Hubbard model, yes, I shouldn't be playing all these games of adding extra terms and now and then and so on. But that's not what I'm trying to do. I'm just trying to write down, understand that there's some general constraints on the theory of what happens when antiferromagnetism appears in the metal. So that's my purpose, and which is similar to the purpose this morning. And as you'll see, it helps to answer some questions, but it's not going to answer the question of what happens in the Hubbard model. Yeah.
So when you added these other terms in phi, which corresponds to force graining,
Yeah.
would there be terms added to the fermionic part of the action too?
Well, so I'm not going to do that because at this point the fermions live at high momentum, so there's not more settled for the fermions. I do have to keep the full momentum dependence of the fermions and their Fermi surface. Later on, so right now this is kind of a hybrid model, but this is in the continuum, this is not on the continuum, this is in the full Brillouin zone. To get something which I have to work a little bit, that's something I want to get to, the so-called hotspot model, where I can even take the continuum limit for the fermion. But at this point, I'm keeping the fermion momentum K to be anything. I'm not doing any gradient expansion for the fermion momentum, but I am making gradient expansion for the phi momentum. Yeah.
I think I was just going to say another maybe point of contact is with the first lecture you had S1 minus S2, so this
Yeah.
a difference.
Right.
And so here you're taking K to be maybe incommensurate, but if you take it to be pi, then you
Right, exactly. That's a good point. So yeah, this tells me that phi is something like, what Leo was saying. What this tells me is that phi is approximately like C dagger sigma I C I e to the I K dot I, and this is C dagger is just S. This is like S1 and then K is pi, and like S1 minus S2 when I take 2 near the other sides. So again, it's very similar to the coupling we had this morning. So I'm just focusing on the staggered spin part, doing some longer than theory for that, but keeping the whole Fermi surface around. So let's now do mean field theory. Okay. And we're going to do mean field theory in phi. So here's some effective potential for phi. So what we know then is that if I just look at this part for phi, that there's some regime where S is greater than 0, where V of phi, again just like this morning, V of phi looks something like this. This is phi, V of phi, this is phi equals 0. And for S less than 0, it looks something like this. Again, phi has 3 components, and all of this part is exactly as this morning. So let's imagine that phi is here and is sitting there. What will the electrons do? What do I see in the electronic sector? Should I close this door?
it may get too hot.
That's too hard, okay. I guess the mic is working. All right, so if I just take phi to be constant, here actually I've allowed phi to have a small momentum q. So q is always small, but k is not necessarily small. So if I now take this coupling here and Fourier transform, write it in Fourier space, then I've got phi q taking you from C dagger k plus q, and then e to the I k dot r factor here means that this electron picks up an extra momentum capital K. And that's where all the interesting things happen, this capital K here. So now, if I take an average, phi equals constant, then my Hamiltonian is a simple Hamiltonian, which is 2 by 2 matrix, which I have to diagonalize. So my Hamiltonian for the electrons now Ck sigma, and then I have this term plus lambda somewhat k. Phi is just a constant, and I take it along the z direction, and so this would be c dagger k sigma c k plus k sigma, and then since the z direction, the factor of sigma here. So I just put phi equals along 0, 0, 1 along the z direction, and so this gives me a sigma z factor, which is sigma here, and that's it. So now I have to determine the eigenstates of this Hamiltonian. I now just use the fact that 2k is the same as 0, because it's 2 pi, 2 pi gives you back to the same position. So in fact, so this term takes you from momentum k to capital K plus k. And then if you apply it again, it will take you from k plus k to k plus 2k, which is the same as k. So you come back to the same point. So you can write this in a 2 by 2 matrix notation. You can write it as, so if I just pick out the terms of little k, I get ek, c dagger k, ck, plus I get ek plus k, c dagger k plus k, ck plus k. I'm dropping all the sigmas here. And then here I'll get plus lambda phi, c dagger k, ck plus k, plus emission conjugate. That's it. So this is just a 2 by 2 matrix. This you can write as ek plus k, lambda phi, and c dagger k plus k, ck. Okay, I haven't crossed this line. Right, so there's just a 2 by 2 matrix which you have to diagonalize, and the eigenvalues of that matrix, are right here. You take the average of the sum of the diagonals, and then this plus or minus the square root of, there should be a square here, sorry. The square of the sum of the square of the differences, it should be a square here. Plus lambda squared by square. It just comes from diagonalizing that Hamiltonian. Okay, so that's the electron new. So the one thing you see is that the effect of antiferromagnetism modifies the electron dispersion. So as far as the electrons are concerned, they want to just occupy the lowest energy states. So you got a new dispersion, they're just going to occupy whatever the new lowest energy states are. And since there's a fixed number of electrons, they're going to occupy as many states as there are electrons. So because the dispersion has changed and the occupied states will also change, the occupied momenta will change, and so the Fermi surface will also change. And that's really the heart of the problem. What happens to the Fermi surface when you are in induced magnetism? So so now you can write a little computer program. You know the chemical potential, you know Ek is some dispersion relation you can write down. You give this to Mathematica and ask it to fill it up and tell you what the Fermi surface is. Okay, I won't go through that. I'll show you a shortcut, but just drawing a few pictures, you can kind of guess what you're going to get. But that's what I'm doing in the next few pictures I'm going to show you. So this is one quick way to think about it. So here's the original Fermi surface. Let's think in terms of holes. So here are the occupied hole states, and here are the empty hole states. So that's Ek. So Ek is equal to 0 everywhere on this line. All right. Now what we know from this term here is that momentum k will mix with k plus capital K. And what are the points I really care about are the Fermi surface points. So the Fermi surface, the Ek is 0, this is the line. This is the sequence, these are all the points where Ek is 0. So now when I look at this, I'm going to mix together with Ek plus capital K. So I also want the points where Ek plus capital K is 0. What are those points? Well, that's easy to figure out. Just translate by capital K. So, and these 4 circles are in the same circle. They're just drawn because the Brouillon's was periodic. I've just drawn 4 pictures of them. So, along this line, EK plus capital K is 0. And along the inner circle, EK is 0. Now let me look at this matrix. So this is 0 along one of the circles. This is 0 on the other circle. So generally, if I pick a random point, either this is 0 or that is 0, or neither are 0. So the eigenvalues will not necessarily shift very much, because if these are non-zero and lambda is small, nothing much will happen. But you know that, if these eigenvalues become equal to each other, and in fact particularly both become 0, then no matter how small lambda is, this is going to be extremely important. The eigenvalues will be plus or minus lambda phi. So the most interesting points are where both are 0. This is 0 and this is 0. And these are these 8 points. These are so-called hotspots, where the matrix is just 0 along the diagonal. So that's a very easy matrix to diagonalize. If this is 0, that's 0. Then this plus or minus lambda phi is, you have 2 levels. This repel each other. So the antiferromagnetism opens a gap. You'll occupy the lowest one with 2 electrons, and the one above you won't occupy. Okay? So what's going to happen is that here, before antiferromagnetism at this point, you had a Fermi surface. We had a 0 energy state. Now, that state gets pushed down. When there's two 0 energy states really, modulo capital K, one gets pushed down, the other gets pushed up. The one combination gets pushed up, the symmetric combination gets pushed up or down depending on the sign of lambda, and the other one gets pushed up. So you open a gap, there's no Fermi surface there. So what happens here, over here, the Fermi surface doesn't remain, and this is what happens. So if I look here, for example, any other point here, the Fermi surface is still there, it just moves a little bit. That's because, one of these 0, the other is not. The effect of this is relatively small, but lambda is small enough. But at these points, no matter how small lambda is, it could be 10 to the minus 10, the Fermi surface will disappear. And there will be a little gap that's going to open up at these points. But this is called Fermi surface reconstruction, where the effect of order doesn't destroy the full Fermi surface, it just opens up a gap and leads to smaller Fermi surfaces, which are called pockets. Now, you might be worried at this point about Leckinger's theorem. You might say, well, didn't you have Leckinger's theorem, which said that volume enclosed by the Fermi surface must equal total density of electrons? And that's obviously can't be true here, because no matter how I count the volume here, that's certainly very different from the volume here, or the area here. One is very small, the other is much larger. So what's going on? So, anybody have a guess?
Spins.
Sorry?
Spins.
Spins partly, but
Your unit 7.
exactly, right. So this, in a lattice, this is not really true. This is equal to modulo 2 per unit cell. I mean, after all, copper has all these electrons in the core. We're not counting those, we're only taking the last shell. So filled bands don't count. Filled bands can always, just be taken out of the game, and they don't count in Leckinger's theorem. So more careful discussion of Leckinger's theorem gives you this mod 2 per unit cell. Yeah.
More generally, the Leckinger theorem is valid just only if you don't have broken symmetry phases, right? I mean, if you break a symmetry, then Leckinger theorem is
right. So there's a Leckinger theorem for every unbroken U1 symmetry. For any time you have, the more formal statement is if you have a conserved charge, any U1 conserved charge, whose value is non-zero in the ground state, then there's a Leckinger theorem associated with it. So in the superfluid, the reason you don't have a Leckinger theorem is because the superfluid U1 is broken, not because they're bosons. You can even get Leckinger theorem for bosonic systems if they don't have broken symmetry. So you're correct. So here, there's conserved charge. There's also conserved SZ. So they are still both conserved, in both phases. So that's a separate issue. There's a separate issue with mod 2 per unit cell. That has to do with the translational symmetry, not the. Okay, so the point is that when I have antiferromagnetism here, and I have this state, then previously this was my Brillouin zone. This is my original Brillouin zone. This is pi minus pi. And now I turn on this kind of potential. So we just think of off-spin electron. The off-spin electrons see a potential which is high here and low there, and so on. So they see a potential that doesn't have the full periodicity of the lattice. And so there's a different periodicity in the new Brillouin zone. This is the new Brillouin zone. So this is called the magnetic Brillouin zone. It's half the size and momentum space of the original Brillouin zone in the presence of antiferromagnetism. And if you look at the area of this Fermi surface, modulo this volume, which is actually 1 and not 2, that is in fact precisely equal, if you did the calculation correctly, to the area over here. But here you have to count these as electrons and these as holes. So these blue regions have negative area and the red regions have positive area. That you see by just looking at how many bands are occupied. So over here you'll find in this region, both of these bands are occupied, and in this region none of them are occupied. So there is still a London theorem, it's more subtle.
So you
But
said
it's
the
still there.
pockets,
Sorry?
the pockets are counted as negative,
That's right. These are counted as negative.
but on the previous, if you go back one slide, one more maybe.
Well, here I'm assuming everything here is negative and everything outside is positive.
Oh, okay.
Okay. That's the geometry in the real system. So that's why they call hole pockets here and electron pockets over there. So this is for very tiny phi. But now imagine increasing phi. So you could, this is at infinitesimal phi. And then you open up gaps in the hot spots. And you keep increasing it. And eventually, these can completely just annihilate and disappear, and you get only the hole pockets. And now the area of these hole pockets must equal the area here inside modulo 1, not modulo 2. And that is really the case. Yeah.
Why does it get smaller when you increase?
Well, because these count as negative in terms of hole volume. So this minus this is equal to just that. Because one has no bands, and both hole bands occupied here, the both hole bands are empty.
No, I mean when you increase pi,
Well, okay, yes. So why does this gap become bigger? Well, that's because these eigenvalues also become bigger, right? So the eigenvalues here. So this is 0, so forget that. It is plus or minus lambda phi. So right at the hotspot, as phi becomes bigger, the gap becomes really big. So you would expect you need a bigger value of this to compensate for that. So this is just mean field theory, pure geometry of and all the amazing things that can happen in this simple exercise of diagonalizing a 2x2 matrix and filling up the occupied states. Here's the same picture again. When phi is from 0, you get a hole and electron pockets, and then when phi is at the same fixed density, phi is larger, you get only hole pockets. Now if you do the same thing with electron doping, then it will be the opposite. The electron pockets will increase, and the hole pockets will disappear. And this will be the evolution with electron doping. And if you're exactly at half filling, then the area of the electron and hole pockets will be equal, and the area inside will be exactly 1. So this will be 1, so 1 mod 1 is 0. And so the point where this shrinks to 0 will also be the point where this shrinks to 0. So you get an insulator, you just need a band insulator with antiferromagnetism. So lanthanum copper oxide is that. Well, at least in this picture with antiferromagnetism. Other people think of lanthanum copper oxide as a mod insulator, where you start from some local correlation. But in real life, it has a very large magnetic moment. And so for many purposes, I think, better to think of it as really an antiferromagnet, a band insulator that doesn't have, because of it's an insulator because of antiferromagnetism, and there's no Fermi surface because of that. Yes?
What if you try to find average of 5 self-consistency? Do you get a non-zero value only from acting?
That depends on parameters, sure. That's not what I'm trying to do right now. Yeah, sure, you can. If you do this kind of mean field theory, you will certainly find regimes that phi is non-zero self-consistently.
So you added some next nearest neighbor hockey to get that not to be a screw diamond?
Yes, yes, yeah. That's absolutely crucial, and that's of course present in the real system.
So that's been measured? That's, okay, I get
Oh,
you.
yeah,
For
yeah.
emission.
Yeah, so that's, I should have emphasized that at this point here. So these TIJs are not necessarily near, it's first, second, and third neighbor, and the values are known, and because you can measure this whole thing, and so you know roughly what the numbers are. Yeah.
Has there been any direct experimental observation about this nodal hole pockets and nodal electron pockets?
So in the electron dope cuprates, sure. So this kind of evolution, I don't have the data here. So let's see. So this kind of evolution has been seen in electron dope pockets. In particular, the electron dope those superconductors, you do see the full pockets for a certain regime. Now for lanthanum copper oxide, for hole doped, certainly this, I think you could say, has been seen. And this, but no one's seen this. And yeah, and I don't think it really is there that you see as you go along. But that seems to be there.
Sorry, that's in which experiments do you have in mind?
Which one?
Which experiments do you have in mind for the hole pockets?
For hole doped?
Yeah.
Well, I don't know. This is very low hole doped. CXGen has various experiments there, I think. They're also quite insulating, but yes. For electron dope, there's Peter Armitage has measurements of these hole pockets in the electron dope side.
One more question.
Yeah.
So for those the hole dope case, by saying people has observed that there should, so do you mean people are sure it is the SDW order or?
Well, I mean, so neutron scattering without question sees antiferromagnetism
Sure.
below around 2%, 2 to 2.5%. There is no question there's antiferromagnetism. There's also an insulator there. So then there's this region between 2% and about 4 or 5% before it goes superconducting. There's definitely some spectral weight in the nodal region. They don't see the backside really, but the intensity there, I haven't drawn the intensity.
That's in clear distinction with the Fermi arcs by.
Okay, that's why I'm hedging, because I think that's a very complicated subject of what's really going on. But I think it's fair to say no one ever seen this pocket. That's never been. That statement I can make. Yeah.
This routine theorem important for high magnetic field where you have sufficient doping and achieve the superconductivity.
In principle, yes. I mean, if you need a lattice potential. If you don't have a lattice potential, then you get Landau levels in quantum Hall states. But if you have a periodic potential at high magnetic fields, in principle, you can just get a metal, and there should be there's a learning lithium there also. Yes.
Sorry, so
Yeah.
momentum is not a good for a number in magnetic field. So
Yes.
how do you define the Fermi surface?
Well, you have a periodic potential, so okay. Well, you're right. Yeah, I was thinking semi-classically there. Wait a second, what was I saying? You have to take some rational fluxes, I suppose, and you're right. No, that doesn't make any sense. I was just thinking semi-classically. Thank you. Sorry. Yes. I mean, if you have rational fluxes, it can make sense. It can be learned the theorem for the Fermi surface volume. Okay, moving on. All right, so what am I going to say next? Right, so now what we want to do is go back to this critical point then, I want to say a bit more about what's happening near this phase transition. This is the phase transition, we have onset of magnetism, or antiferromagnetism. And what's new here from this morning lecture is that at the same point, because of the presence of these hotspots, you have a reconstruction of the Fermi surface. And we really have to take that into account because this is something happening at very low energy, so it's not something I can just throw away and just force grain away. I have to really worry about it much more carefully. So the way we're going to do that then is by taking a continuum limit, and we're going to focus in on precisely these 8 regions. So you focus in on these hotspots, and we're going to blow up our momentum space and pick one of these hotspots and really zoom in to that region. Okay. So now if I go into this region here, I can make a lot of very useful approximations. So I have this one Fermi line coming in here. That's this is E of k. Sorry, I should put that back in. And then I have another Fermi surface associated with E of k plus k. So that's this other Fermi surface, which is really over here, which is this point moved over by pi, and that's E of k plus k equals 0. So this is the line where E k is 0, this is the line where E k plus k is 0. So what I can do is, first of all, I'll rotate that by 45 degrees and write it this way. So now what I'm going to say now is that E of k, I'm going to say that E of k is approximately V dot k minus k hotspot. So let's take this line here. So it has some. This line here is the same as one of these lines over there. So it vanishes along this. E of k vanishes along this line. It only depends on the direction orthogonal to this, which I'll label by the vector v1, and vanishes at this point. So E of k is just going to be some v1 dot k minus k hotspot. And similarly, E of k plus k will be v2, which is some other angle, dot k minus k hotspot. So you expand them around the same point, and they give you 2 velocities. Okay, so we're going to take this 2 by 2 matrix and just approximate both of these functions by 0 plus a linear function of k. And the linear function of k has only varies along one direction orthogonal to the Fermi surface. So these are not direct fermions. In direct fermions, you've got multiple components and gamma matrices. Here, it really just depends on one component. Each one of them depends on only one component. Okay, so that will be my theory now. It's going to be, so now I can rewrite, this is the typical way of writing it. I have electron species 1 with velocity v1, with this v1 dot delta, and electron species 2 with velocity v2. I haven't said anything. Yeah, let's say we're starting on the disorder side. But the whole formalism can work on both sides. Well, so that I'm going to allow then for this coupling and then also this coupling. So now this coupling here is exactly, where did it go? Well, exactly that coupling. It becomes very simple. It just becomes phi dot psi dagger 1, psi 2, the sigma matrix is thrown in, and this is the geometry. Okay. So everyone with me here? All right, so now we're going to do some honest perturbation theory. So this is now the same theory. Now if I put phi equals constant, as this shows, so now if I put phi equals constant, then this will give me an off-diagonal term. I re-diagonalize this matrix in this language, and these Fermi lines where E of k is equal to 0 will become, open up a gap and give you the electron and hole pockets. Yeah, it's geometrically hard to absorb the first time you see it, but it's really, as you can see, it's nothing more or less than just diagonalizing, than looking at the properties of this dispersion.
decide you want to only focus on the constants?
That's where you're doing the maximum damage to the Fermi surface, if you wish. I'm sorry?
To the Fermi surface.
Yes. Well, you anticipated that's where something similar is going to happen when I look at the effect of the fermions of the boson, which is what my next slide is going to be. But that's the point where the Fermi surface goes from this line to this parabola. There's the most singular effect exactly at that point. If I focus here, the Fermi surface is approximately the same. It doesn't change very much. So you don't expect the other parts of the Fermi surface to be really that crucial. Well, to make a relevant versus irrelevant argument, I need a field theory first. I don't have a field theory yet, because I have all these large momenta floating around. So I will have to have some continuum theory which I can rescale. And that's what I'm trying to do to get such a theory. And once you get such a theory, then you can start making such arguments. So at this point, I don't have that ability. Okay, so let me just work with this theory. Oops, yeah, here's the theory. And as I said earlier, if you're not familiar with pattern integrals of fermions, think of this as the Hamiltonian v1 dot grad for psi 1 and v2 dot grad for psi 2. So what we're going to do now is do perturbation theory in lambda. We're going to be in the metallic side, the non-magnetic side, and just do perturbation theory in lambda. So that's this particular graph. So here's my phi. Phi creates a particle hole pair. So this is just the kind of calculation you do in producing the dielectric function of an electron gas. Except now, to simplify things, these fermions in this loop have dispersion v1 dot k and v2 dot k. Okay, so all I'm doing here is so if I take my Hamiltonian is sum on k over such a different color. Sum on k v1 dot k sine negative 1 sine 1. Let me not write down the spin indices. That's v2 dot k times sine negative 2 sine 2. And then I have a term plus lambda phi sine negative 1 sine 2 plus energy quantity. Now I just compute the change in the energy. So if phi is constant, I want to compute the change in the energy due to phi. At second order in perturbation theory, I have to evaluate this graph. Where I have a phi here and a phi here. And I pick up a vector lambda here, lambda here. And this is say v1 dot k, and this is v2 dot k. Now phi has momentum q, this will be v2 of k plus q. So that's what you do diagrammatically here. This is done using Matsuburg frequencies. So the electron Green's function is minus I epsilon plus v2 dot k. And that's for psi 2 and that's for psi 1. And then I've also allowed for the external phi to have both space and time dependent. So it's just like when you compute the dielectric constant. Initially you think of the dielectric constant as a constant. Then you learn in many-body theory the dielectric constant is actually a function of q and omega. So here also the free energy, the effect of the electrons on the phi, which is assumed to be a function of space and time, is like some external potential acting on the electrons, and this is the induced effect of the electrons on the fluctuation of phi. All right, so now it's a matter of doing this integral. This is a kind of integral that is just a variant of the Lindhard function, being evaluated in a different regime for a certain special dispersion. You can read Fred and Valeska how this is done in great generality, or you can read these few lines to see how it's done very simply for these particular dispersions. I'll just leave it there for you, and this is the final answer. Okay, so we want to now interpret what the meaning of that answer is. And to answer your question, it's the most important feature of this is this mod omega term. And that comes entirely from the vicinity of the hotspots. It comes from that part of the Fermi circuit, which is why that's where, and this is a much more, this is a very important term, and that's why I have to focus in on the vicinity of the maximum. Yeah.
I think this is zero temperature.
Yes.
Final
Yes.
temperature will be square root of omega squared or something like that. Plus p squared.
Yes. Yes. Something like that. I don't remember. Okay. So what we've done here is I started out just as this morning with a bunch of harmonic oscillators described in my autograph. So I had d phi d tau squared plus grad phi squared plus some phi squared. I'm treating this coefficient to get across the phase transition and the phi to the fourth term. And so in Fourier space, I can write this as omega squared phi squared plus k squared phi squared. Now what I've done here is this is for an insulator. Now what I've done here in this graph is taken into account the effect of the Fermi surface. So the Fermi surface, it induces some time-dependent effective potential for the phi. So I have a term here, which is basically, roughly speaking, because of the Fermi surface, minus pi times phi squared. And so that becomes, when you plug this in here, this is just some constant. And so what you find is plus mod omega times phi squared. And the coefficient here, which goes is lambda squared. And some other things that depend on V1 cross V2. So the whole purpose of this exercise is to now ask, what is this? So this term is sometimes called Landau damping. It's a term that tells you that these harmonic oscillators that you had before are actually overdamped. Now this is an imaginary time, so this is imaginary time. This is imaginary time. And so in real time, or real frequencies, roughly speaking, this is omega squared plus minus omega squared plus k squared plus, or I think it's minus, I don't remember, minus I lambda squared omega. So previously I had as omega squared minus k squared, that has a pole at omega equals k. Oh, sorry, there's also a term here, just this. So let's keep that as here. So this was what I had this morning. This is the triplon, or the paramagnon, spin one particle just completely undamped until it hit another paramagnon. Now what's happening here, what this is showing you, is your triplon can come along and has a damping. And what this is telling you, the triplon just decays into a sea of particle-hole pairs. So you have this Fermi surface, it can easily absorb spin 1 by creating a particle-hole pair that carries spin 1. And we're just computing the density of states for the triplon to decay into the particle-hole pairs of quasi-particles near the Fermi surface. And the density of states is what this graph computes, and that tells you that it's actually independent of momentum k, and it's just some linear density of states, which in the harmonic oscillator language, this is just like a damping term. So it's a damped harmonic oscillator, and at low enough frequencies, it's overdamped because this term is always more important than that. Right. So the effect of the Fermi surface is to damp out your triplon. Your triplon becomes a broad excitation, and it's not a coherent particle that can live forever, as was the case in the insulator this morning. So that's one of the most important differences between the insulator and the metal. Yeah.
Maybe this is too much details, but I think even if you transform to real time,
Yeah.
I think it's still absolute value of them.
Okay, so this is for retarded functions. It's no absolute value. The absolute value is for the Matsubara functions. Okay, so you have to do all these analytic considerations carefully. But if you're talking about retarded function, it's not absolute value. This is the retarded response function. Yeah. So that always has its poles in the lower half.
But the position, if you don't have absolute value, the pole will depend.
Yeah.
Whether it's in upper or lower
Yeah, so
half
this-
will depend on the sign of omega.
Yes. So you're coming to, so in the complex omega plane, what I computed there was the function along this axis. And if I want the function on the real axis, I have to come this way. That's called the retarded function, and what I'm plotting here is the retarded function. If I want to come this way, then I get the advanced function with the plus I omega. but it depends on which side of the axis you're on, not on the sign of omega. Now, if you want to get a time-ordered function, that's a more complicated thing, and it can have sine omega there. But on the real axis, I'm talking about retarded and advanced functions. Yeah. Well, on the imaginary axis, it's time-ordered. Yeah.
This is, I guess, a question outside the domain of critical theory, but even with this, would the higher momentum and thus higher energy triplons be sharper then? Would they not be able to decay into particle fold pairs?
No, I don't think so. I think there's always particle pairs around it. It will depend on the full geometry of the Fermi surface. You wouldn't be able to focus in on the hotspots. Anyway, so this is called the Hertz action then for the onset of antiferromagnetism in a metal, where he pointed out that unlike a regular relativistic field theory where you have an omega squared term here, you have a mod omega term. So that was a pioneering paper I heard in the late 70s, I think. And his conclusion, after he came to this result, was that quantum critical phenomena of fermions was not that interesting. And the reason for this is this exercise that I will leave to you. So what, roughly speaking, what did Hertz show? Or how did he argue? So he argued that, so if I look at this, each power omega behaves like 2 powers of k. So roughly speaking, each time dimension looks like 2 spatial dimensions. And so if you do the usual renormalization group analysis for this coupling U, which I won't do, you'll find that this flow of U is like a theory not in d plus 1 space-time dimension, but d plus 2 space-time dimension. So in 2 spatial dimensions, this would have the RG flow of the usual 5-4 theory for an insulator in 4 dimensions. Sorry, the usual classical 5-4 field theory in 4 dimensions, or an insulator, quantum insulator in 3 dimensions. And in 4 dimensions, we know mean field theory approximately applies. So Hertz concluded that the transition in 2 dimensions is approximately mean field, and in 3 dimensions it certainly is mean field. Okay, so that some of that is correct, but a lot of that is not correct, especially in 2 dimensions. That's the topic for my last lecture, but I'll say much more about this. There's many ways of understanding it, but this whole procedure of just assuming that you can get rid of the electrons and write down a theory for the phase transition in terms of just the boson is not a valid one. It works in high enough dimensions, but it doesn't work in 2. And you really have to work with a field theory that includes both the electrons and the phi at all stages. And we understand how to do that much better today. And I'll say a few things about it in my last lecture. But the main physical effect I wanted to introduce here was the idea of Landau damping. Right? You can have these collective antiferromagnetic or paramagnon fluctuations which have a finite lifetime because they can decay into particle-hole pairs that can run off along different directions. So if you create a spin fluctuation, a neutron comes in an insulator, creates a triplon when it flips, and an insulator, that triplon in principle moves on a straight line forever, like a particle, low enough temperature. But in a metal, a neutron can create a triplon, and even at 0 temperature, that triplon will just dissipate away into lots of particles and holes going off in all different directions. So there's nothing really coherent left over. But that's Landau damping. And one consequence of that, according to Hertz, is that the critical phenomena is not that interesting. It's just approximately mean field. So that's the main conclusion. Yeah?
So a lot of times you see omega over q. Is this q equals to k in this case?
Capital K, yes, roughly speaking, yeah, which is a constant. So this is for
You
antiferromagnetism.
don't see this once you go to these hotspots theory. I mean, in order to see that, you have to do the full.
No, so the omega over q comes for other order, like ferromagnetic order parameter, not antiferromagnetic. So as long as V1 is not parallel to V2, It's just about omega. So did you notice this is in the denominator here? So when V1 becomes parallel to V2, things singular.
Right, but what I mean is, if you wanted to see that it's really omega over capital K.
Roughly, it's not exactly, yeah.
Right, but you have to keep, you have to keep the full Fermi circles, not just the hot spots.
Yeah, I mean, you can think of what pi, I mean, it's just a question of what you're measuring Q from. I'm measuring Q from capital K, because if you measure your magnetic fluctuation from the center of the Brillouin zone, then this Q is a very large Q. That's all. It's just a question of where you put your low momentum for the auto parameter.
And for terminate, K is 0, and so you need.
Yeah. So I'll come to that case in my last lecture, but that's a simpler case. All right. So this is one new piece of physics, but there's another very interesting new piece of physics. In this case, not very new, which is superconductivity. So what I've been talking about so far is the onset of antiferromagnetism in a metal, and now there have been various arguments, and we have now pretty good evidence that actually this critical point doesn't even exist. That in this region, it's always a superconductor. So the argument of this goes back to this paper by Scalapino et al. This is before the discovery of ITC, where they mentioned dx squared minus spin singlet, dx squared minus white pairing on the three-dimensional Hubbard model. They just didn't have the courage to think about the two-dimensional Hubbard model, but anyway. So that's pretty remarkable. And so the arguments are actually very similar to the kind of arguments that Andy started to review this morning. And I'll present those arguments in a slightly different language for my purposes, to prepare for what I talk about tomorrow. All right, so here's the Fermi surface geometry. So now I want to focus on this region. And what we have seen is that near the hotspots, you have this coupling between electrons here and here, which we can think of as a coupling due to paramagnon or tripton exchange. So there's this overdamped particle, but it's still there. There's some excitation with a very large susceptibility, which we call phi, and it interacts between electrons here and here. Now, just as BCS taught us, when you have a phonon, you have some boson that induces an attractive interaction. So here you have a spin 1 boson, spin 1 overdamped boson, variously called a paramagnon or a triplon, and that can also induce an attractive interaction. But because of the spin structure and other features that Andy was discussing and which Scalapino et al. Also discussed, what you get is D-wave spin singlet superconductivity.
Sorry.
Yes?
If you're going to get superconductivity from this eventually,
yeah,
you won't get lambda damping.
Well, right. So this is I'm just reviewing the simple mean field argument at the moment.
Okay.
This is not a proof that it exists.
Okay.
Yes, of course. I'll come to that point in a minute. That's the, as you probably heard me talk about it before. Okay. So right now I'm just reviewing the arguments that Andy was doing this morning and arguments that Scalapino et al. Gave in a slightly different language. Yeah.
One question about, so if I'm in a paramagnetic state,
yeah,
how should I think of, then I can't shift my Fermi circle. There's no meaning of shifting Fermi circle by K.
No, I mean, so the way to think about it is I have a big Fermi surface.
So I'm just asking the question, the meaning of psi 1 and psi 2.
Yeah, no, psi 1 and psi 2 are going to vanish for a little while, as you'll see. I don't have to work with psi 1 and psi 2. I have a Fermi surface here, so there's low energy fermions here. Then I can also do neutron scattering, and I can measure S of K and omega, its dynamic spin structure factor, as a function of K. And some low frequencies I find it has a huge peak near capital P. Now, so just for convenience now, I call this peak as some overdamped particle, and I measure my momentum from this point rather than from this point. That's all I'm doing. Okay, I have to have the full Fermi surface and have this boson that's overdamped and carries momentum capital K. Let me write down the Hamiltonian, that's the next slide.
So that part I understand. I guess you wanted your field, I thought you wanted your field theory of the boson, triplon, and the fermions to work on both sides of the critical point. And I'm asking about how should I think of it on the paramagnetic side, the fermionic sector?
I am in the paramagnetic side. You mean on this side?
On the paramagnetic side, how should I think of the fermionic sector of it, where I've done this? I looked at side 1 and side 2 on the paramagnetic side.
Oh, well, I should just go back to this picture. I mean, so right now, this is just this Fermi surface reproduced, and then I just zoom in on that point. So when I write down the theory for this point, I effectively have the theory for this portion of the Fermi surface and this portion of the Fermi surface, or this one. Sorry. So I take my big Fermi surface and I just take little patches of it, and I have a theory for 2 patches. That's all.
I didn't miss it. So these circles are shifted by
K. Yes. Pi pi. They're shifted by pi pi. So you have the original Fermi surface and then the image of it, and then I just zoom in on that point. And when I do that, I'm still on the paramagnetic side. I'm just giving a theory for this patch and that patch. That's it. So I have 4 pairs of patches. I cut the Fermi surface up into 8 patches, and I write on 4 theories, 1 for each pair. So it's just a bookkeeping device of how keeping track of different parts of the Fermi surface. Of course, I'm ignoring the difficulties of what happens when they meet each other. That's a little tricky, of course, and you do have to worry about that. Good. All right. But I think part of the confusion here is I'm going back and forth between many different things. So I've introduced the hotspot model. The reason I introduced it here was just, to me, it's the simplest way to understand where this model omega comes from, and here's the calculation that gives it to you. Okay, and I'm still completely on the paramagnetic side. Okay, still, maybe Steve, you can explain to everyone, since I'm obviously not doing a good enough job.
No, I'm just saying, it's a big Fermi surface with coupled to a boson that's going soft at a particular wavelength.
Yes, that's the picture I drew here, right? And then I can just take the big Fermi surface. So what I do is I have this Fermi surface. I can just split it apart into 8 pieces. And I just say this is from side 1, this is side 2, and I just write down theory for this, and this, and this, and this. And I ignore the difficulties of what happens when they start to overlap. That's the only approximation I'm making. Okay, so now forget all of that. Let's take this picture. I have a big Fermi surface. I have a boson which is fluctuating most strongly at momentum capital K. And then I assume that boson induces some interaction between the electrons. So that would going to give me that's this kind of process. Here, one electron goes in here, another electron goes in there, and there's a boson in between. And so that gives me an interaction, spin-spin interaction between the electrons. This is what Andy this morning called Vs. We had a V rho and a Vs. This is exactly Vs. I assume Vs is peaked at capital K. So now Q is being measured from 0 with some width given by some correlation. We are just taking a particular form of V of Q, which is I think what Andy will do also when he discusses this on tomorrow.
Is there frequency dependent?
Not in this calculation. Right now I'm just doing mean field VCS. So this is basically the argument in Scalapino et al.'s paper. So now I perform the mean field decoupling, exactly what Andy went through this morning. And when you do that, you get the gap equation. Here's the factor of 3 that Andy was mentioning. I don't have a V rho, I only have a Vs, and that's the 3 that comes in. And the most important feature of this gap equation is this minus sign and this capital K. So what this is telling you, the minus sign comes from the spin, the fact it's a spin 1 propagator. In the usual phonon BCS equation, there is no minus sign here, and this sign is also not there. And you get some, this capital K is not there, you get the usual BCS solution for this. So now, the difference here is the capital K and the minus sign. And what this tells me is that this thing is only very important when P minus K is close to capital K. So what I want is delta K and delta P to have opposite signs when their difference is capital K. So when this is large, I want this to have the opposite sign from that. That will get rid of this minus sign. Okay. And I think Andy will go through that in more careful detail than I have here, but all the equations are there. So if we just put this on the computer and solve this equation for delta K, the pairing amplitude, you'll get a solution which, to excellent approximation, looks like a D-wave solution. And the reason it's D-wave now is that if you take an electron here at this hotspot, then you add capital K to it, it moves here. And what the requirement is that the gap must same sign when it moves by capital K. So what's positive delta here when it add capital K must become minus delta. So it's minus delta along here and plus delta over there. And why is it plus delta here? Well, that's simply because that's the hotspot theory won't tell you that, but the nearby and only has roughly the same sign, the same region of the Brillouin zone. So if you solve this whole thing around the Fermi surface, you will get a D-wave solution. Okay.
So it's D-wave, but not necessarily proportional to that first harmonic of D-wave.
Sure. When Xi, as you pointed out, when Xi becomes very large, then there can be deviations from that. And here's another picture of the same thing. I have two electrons coming in. They exchange the boson phi. Usually they exchange the phonon. Now, for them to interact strongly with this boson, A and B should be separated by capital K. That's why A is here. Oh, sorry. These are couple pair. So these are K and minus K, A and B. Now, when it emits a boson phi, A and C should be separated by capital K. So A and C. So A emits a boson phi and gets scattered to C, and B absorbs a boson phi and gets scattered to D. So A, B gets converted to CD, and they must flip their sign, so that's why this is red and that's green. So it's positive, negative, negative. Okay? So that's the same picture here, showing how you get D-wave pairing due to antiferromagnetic interactions. Alright, so this is just a mean field theory. And as Sam keeps insisting, why should I believe this theory? And I agree. So, you could have said in 1987, here's the theory, declare victory, and ITC solved. Well, okay. So well, maybe some people said that, but why wasn't that immediately accepted? Maybe we should have accepted it, but anyway, it wasn't for sure. So what's missing here from this calculation? Well, first of all, it's a mean field calculation. And now, when it all built upon this exchange of boson near the hotspot, that's where the strongest attraction is. So we really have to focus in, whether you like the hotspots or not. If you want to really understand this theory, you have to focus in on them and see what's going on. And if you look at that theory, and this is what I haven't shown, Hertz argued that the theory of essentially weakly coupled in D equals 2. That turns out not to be correct. It in fact flows to infinite coupling, and you need new types of ideas on how to solve it. And you have no, that's not you, that's the other guy. Sorry, I apologize. But Sunsig has a very nice paper of one way to do that, which I won't discuss, but it has a not so nice feature that it suppresses the superconductivity. But anyway, so we can't really believe this perturbation because the coupling becomes very strong. You'll say, well, oh, that's great. The coupling is strong, the attraction is even stronger. So let's explain ITC. So that's the positive view on it. Yes, it's a very strong coupling. It becomes even stronger in RG. I haven't shown you how. So yeah, explain not only low TC but also high TC. Okay, so you can be very happy. But what I've left out here, that this very strong coupling has other effects. So far, I'm just assuming that the effect of the phi boson is to induce an attraction between the electrons. That's certainly true. Near the hotspot, it induces a very strong attraction. But it does other things. It also scatters the particles. So you can also get terms like this, where you have an electron going by, and it emits one of these phis. So the quasi-particle gets scattered. Now if you want to compute the lifetime, then you have to do, in Green's function language, you have to compute this graph and look at the imaginary part. If the emission, the imaginary part of this is cut it in half, it's an electron that's decaying into a boson. And when you compute that, you find that it in fact leads to the breakdown of the quasi-particle. So you have this difficulty. You say that there's a very strong attraction of quasi-particles, but you look more carefully, you find the quasi-particles don't actually exist. So this is not good for superconductivity, because the things that are forming the Cooper pairs don't really exist. And so that's an effect in the opposite direction. So that's one of the effects. And again, you can do this calculation, even if it's not clear immediately which is going to win. And as I'll discuss a bit tomorrow, that's not the end of the story. And all we're doing with this, we started out with this very innocent question. Tell me what happens when an antiferromagnetism has an onset in the metal. So Hertz said, not much. And Scalapino et al. Said superconductivity. And as we'll see tomorrow, that's not the end of the story. There can be other things too can happen. And these can interfere with superconductivity. And so this is supposed to be leaving you confused at the end. You don't know the answer of what the final answer is. Okay. All right, so how much time? I have about 10 minutes?
About 10 minutes, yeah.
Anyway, so in the remaining 10 minutes, I want to talk about some recent work where we address this issue using quantum Monte Carlo. And the narrow issue we addressed, can a model with hotspots, can a model of fermions, when you go from a metal to an antiferromagnetic metal, can you answer yes or no whether there's superconductivity in between? And you go across the quantum critical point. Across this point, we have all these strong coupling effects. And the answer, to give the punchline, is the answer is yes. You do get superconductivity. We have very good evidence for it in a model for the onset of antiferromagnetism in a metal. But anyway, so I'll pause for more questions before I describe this. I won't give all the details here, but just show you the results of the quantum Monte Carlo. Yeah.
Maybe to put your talk in connection with what Steve was talking last week.
Oh yes, I understand.
If correlation length is not very large, if you are not close to a critical point,
yeah,
then I guess I have little doubt that some superconductivity of D-wave type appears. So the question is whether it's larger.
Yeah, does it high temperature superconductivity? Yeah, I mean, certainly exponentially small PC everyone accepts. That's the leading weak coupling. But as you get to stronger coupling, does it survive until it can give you ITC? That this calculation doesn't address.
If I assume a charge sample is dirty, and consider the coupling of those magnetic modes not to the electron degrees of freedom, but to collective diffusive modes, to diffusons, what would be the critical properties of such model, can you say?
You mean diffusions of what? Of the antiferromagnetic fluctuations?
We have antiferromagnetic fluctuations.
Yeah,
they are coupled to diffusons.
Not literally.
Well, diffusons are this normal diffusons have zero momentum. That they're the ferromagnetic part of the dense. Q equals 0. That's where total spin is conserved.
In our orders, there will be some coupling.
I don't think that's terribly important. I mean, the effects of disorder are certainly extremely important and not well understood. The most important term here in disorder is the effect of disorder on the phi squared term, just the position of the critical point. That's believed to be relevant. I think that's the most important effect. The coupling with the ferromagnetic sector, I don't think is that important.
Also, there will be some renormalization of the antiferromagnets, even without coupling.
Yeah.
For example, like don't.
Well, my guess is that the antiferromagnetic sector doesn't care much about diffusons because it's really at final. Because the antiferromagnetic autogram is not a conserved quantity. It's not like ferromagnetism. Ferromagnetism, I agree, to be much that's something Kirkpatrick and Dulles have studied, the interplay between diffusons and ferromagnetic critical fluctuations. But for antiferromagnetism, I don't think it's as important. Any other questions? Okay, so I'll talk about my recent work with Erzberg and Max Metlitsky. So we asked the following question. Can you write down any model for which you can convincingly show the following things? In one regime you have a metal, probably with a very exponentially small TC. Another regime you have an antiferromagnetic metal, also probably with an exponentially small TC. And you have an antiferromagnetic critical point between them. And in between, is there strong superconductivity? And what is the fate of this hotspot physics? So, of course, you could just take the Hubbard model and put it in a computer, but nobody can do that. That's too hard because of the sign problem and other issues. So we said, okay, let's make the following, this is the following logic here. Let's believe this whole hotspot approach. And certainly, if there is an antiferromagnetic critical point, those are certainly the most important parts of the Fermi surface. So suppose I want to study the onset of antiferromagnetism in this Fermi surface. And I spent the whole lecture arguing that all the interesting things happen near these 8 points. So allow me the freedom to change the Fermi surface away from those points. So I'm going to take this Fermi surface and change it to this Fermi surface. So if you look near those points, nothing much happened. But away from those points, I have actually reconnected this part of the Fermi surface with that one, other than connecting it here. So I've done a topological change in the Fermi surface. It's reconnecting portion of the Fermi surface far away. And the only reason I've done this is because this allows you to, this particular model now, if you write down on a computer, has no sign problem. Without any further assumptions, just have to reconnect the Fermi surface and you can take any shape you want otherwise. And if you have time reversal symmetry, you can show that this model, this particular theory for the onset of antiferromagnetism has no sign problem. So if I believe that all of the interesting physics is near the hotspots, the claim then is I can take the hotspot theory of Ivanov and Chukukov and put it on a computer without a sign problem. So we're just solving the hotspot theory by a convenient lattice regularization. We're just cleverly choosing the lattice regularization of the hotspot theory to get rid of all the sign problem. So that's requires only time reversal symmetry. You don't need any other symmetries or particle Hall or anything else. You take any density you want, and it just requires that you have 2 bands, and the hotspot in one band always connect to the hotspot in the other band, which is a feature of this particular band structure. So what's happened to my original model that I talked about earlier, I have electrons in one band coupling to the bosonic autoparameter phi. Now in this new theory I have 2 bands, the X band and the Y bands, and the phi coupled always flips X to Y. So you only have inter-band interaction, you don't have intra-band. But as far as the hotspot theory is concerned, this is completely generic. So here's the theory we can solve on the computer, which we know we're very confident will have onset of antiferromagnetism, and which has all of the physics of hotspots. It has the physics of quasi-particle damping, it has the physics of strong interaction, attraction, and so on and so forth. It really has everything except at low energies, but the set of parameters that we are allowed to put in are sort of limited because we are only allowed to have inter-band exchange interactions. All right, so, and actually this is not such a ridiculous thing. Models like this are quite appropriate for the ion-based superconductors too. All right, so now I'm going to show you the results and then I'll stop. So just to show you the results, just to plot them, we want to things get confusing with these many bands. You want to move things around a little bit. So what I'm going to do is I'm going to take, what did I do? First of all, what did I do? Yeah, I just moved that point over here. So nothing has changed, I just moved everything by pi. And then I'm going to take the red band and move it over by k. So here. So just move the red band over by k. This is just for ease of plotting. And once you've done all of this, you see now you have 4 hotspots which are all going to open up again. So when you have antiferromagnetism, the Fermi surface will change from this to this. So those are my electron and hole pockets, and this is the full system. So you take the system, you put it on a computer, I should say it's all done by Ayres. This is many months of very careful work. And here is a picture of the Fermi surface as you tune the coefficient of phi squared. So this is when R is large and positive, this is the antiferromagnetic metal with these hot spots there. And then when R becomes negative, you get antiferromagnetism, and the Fermi surface reconstructs, and the hole pockets eventually disappear, and you only have electron pockets in this geometry. So you get Fermi surface reconstruction very beautifully. And, you kind of built that into the whole model. But then you can also, by doing various critical phenomena type things, figure out where the quantum critical point is. So there is a point around 0.25 then, R equals 0.25, we have one set of antiferromagnetism. So one side is antiferromagnetic and the other side is not. And then finally, you can go and look for superconductivity. You didn't put it in, you just look for superconductivity across the quantum critical point. And here's the quantum critical point. And you see that the superconductivity actually is roughly maximum pretty close to it, and it's D wave. This comes out, we looked at other possibilities, it's all very much suppressed. And so this is then fairly convincing evidence for us for the existence of superconductivity peaking at the antiferromagnetic critical point in this particular lattice realization. So, okay, so so it does win, and it does give you reasonably large superconductivity. This is, you take the square root of this to get the gap, because this is a 2-point correlation function, and that's quite a reasonable value, healthy value compared to the Fermi surface. Yeah.
So this was a non-interacting theory on the right.
Sorry?
If this was a non-interacting theory on the right, what would this susceptibility look like?
Non-interacting theory of what?
On the right.
This isn't susceptibility.
The pair susceptibility. This is the, I don't know. I wouldn't. Sorry?
Would it diverge?
Well, it has a log divergence, sure. It has a log divergence, sure. Yeah. Yeah.
You can here the. Wait a second. As a function of R, it cannot do anything. Yeah.
That's
but
right.
It's a field. It's only
That's
a
right.
constant.
That's right. Yeah. Sure.
Well, you always deal with finite systems, so.
This is a finite size system.
Log is always constant. So it will be some constant.
Yeah.
What's the conclusion about superconductivity around the
Well, that's where it's strongest. So this is the pairing amplitude, and it's strongest for the largest system size we have, right near the quantum critical point.
So you have like superconductivity onset with information around.
Yeah, well, we have to study a little more carefully exactly where it is, but it seems to be more on the paramagnetic side than the ordered side. In fact, it seems to be shifted a little bit to the right, and we also kind of suspect of that. Okay, so then to conclude today's lecture, what I reviewed today was first the mean field theory for the onset of antiferromagnetism in the metal. It leads to this kind of Fermi surface reconstruction at the same point that you get the onset of antiferromagnetism. And what we found that as you approach the critical point, in this region, there seems to be D-wave superconductivity. Of course, it's there really everywhere, but out here it's exponentially small, so you would never see it in any of the finite size systems we're looking at. But it seems to be pretty well formed right near the antiferromagnetic critical point. Yeah.
Is there indication of that exponential fall off on the ferromagnetic side in the quantum Monte Carlo? It seemed like it was flattening out.
Well, okay, it's a relatively small system size, so we have to eventually things will go down. I mean, there's a fairly strong attractive interaction even over here. Maybe R is not, maybe you have to make it much larger. Yeah, this is all under, I guess as you know, there's a lot of additional work being done to flesh out all the quantities here. All right, so I think I just stopped right there. Yeah.
Thanks very much. Okay, great. Don't forget, we have 15 minutes break, not half an hour break. So next lecture.